We're going to do some implicit differentiation problems that look a tiny bit different than what we were doing before, but really follow all the same processes. But the reason that we're going to do these is because there's going to lead us into word problems called related rate problems, which we'll see in class. So in this problem, we have x and y, and they're both functions of t. And so this is the piece that is different from what we've done before with implicit differentiation. In our implicit differentiation problem before, we've thought of y being a function of x. So we've thought of this as y is equal to some function of x. Now that's not what we're thinking of. We're thinking of y as some function of t, and x is also some function of t, but probably a different function. Okay, and maybe let's write this instead of f and g, let's make this y of t and g of t, just so, or an x of t, just so we have the same letters. So when we take a derivative of something that has an x in it, we're going to get a dx dt as well. So let's think about that before we start doing these problems. So if I had something like x squared, we could really think of that as x of t squared. And now we have a function inside of a function. So we need chain rule. My outside function is x squared. My inside function is x of t. The derivative of x squared is 2x. The derivative of x of t is dx dt. And so we put this all back together, we get 2x of t dx dt. So that's like 2x dx dt. So we notice that now, because x is a function of another variable, this is behaving like y behaved when we were doing implicit differentiation before, where whenever we differentiate something that has either an x or a y, we're going to get an extra dx dt or a dextra dy dt. Okay, and that's because now we're thinking of x and y both as functions of a third variable. Okay, so let's see if we can do this, and we'll do examples like this in class. So if these get a little confusing, just ask me. I think sometimes it's more confusing because we're using the variable x, and x being a function of t, but I'm purposely doing that because if we can understand it with x, then we'll understand it with whatever letter we use. So let's look at the cosine of x squared. We're going to need a chain rule on that. My outside function there is cosine of x. My inside function is x squared. Cosine just becomes negative sine x like always. But x squared we just saw becomes 2x dx dt. Okay, so when we start, we're going to have that's going to give us negative sine of x squared times 2x dx dt. Okay, now we can differentiate the 3y cubed. So 3y cubed is going to become 9y squared dy dt. Remember, this is no longer dy dx, it's dy dt because y is a function of t. Let's see, that piece is going to need a product rule. So we're going to have, we can think of this 2x times y. So 2x is going to be 2 dx dt because the derivative of x now is dx dt. And we leave the y alone. Then we leave the 2x alone and we'll have dy dt. And then the 4 goes away because its derivative is 0. Okay. So in this particular problem, we are not trying to solve for dx dt or dy dt right now. We have things to plug in. And the reason we're plugging numbers in here is because when we do these related rate problems down the road, we're going to have numbers to plug into them. So this tells me that x is 0 and y is 1. It tells me that t is 1, but we're not actually going to use t in this problem at all, which is all right. So let's see, if x is 0, this whole piece will go away. And this whole piece will go away. So we're going to have a 0 is equal to y is 1. So that will be 1 and that will be 1. And then let's see, dy dt is 2. So this piece will be 2. So we're going to get 9 times 1 squared times 2, which will give me 18. And then we want to find dx dt. So this is the thing we're going to find. So we're going to have 2 times dx dt. So we can subtract 18, divide by 2. So dx dt is negative 9. Okay. In this particular problem, we don't know what that means. This -9 isn't necessarily telling us anything super interesting. But when we do related rates problems, this might be telling us how quickly the radius of a circle is changing or how quickly the diameter of a balloon is changing. It will all depend on the context of the problem. But for now, we'll understand how to do these more abstract problems, and then we'll put some words to these types of problems.